Now let us study about some basic properties of magnets. Okay, the first one is magnetic dipole moment. Okay, let's take a magnet here like this way. Here. So there are two poles in north pole and the south pole. We know. Okay, so this is the middle of that, and then let from this distance, from middle to this distance, be L. So this distance also will be L only. Okay, the total distance here will be 2L. Okay, 2L you can also see it as D also. Okay, we get it as D. Now we can define the magnet dipole moment. Okay, so we have the magnet dipole moment symbol is Pm. Okay, this time it's a vector quantity. Okay, it's equal to the pole strength. Qm means pole strength into the distance here. Okay, so what does the term mean? This term Pm means the magnetic dipole moment. Okay, that's a symbol there. Then Qm means the pole strength. That means the strength of each magnetic pole. Okay, so pole strength, and D is the distance between the poles. Okay, distance between the poles. Okay. So this is the formula that we use in this case. Okay. So now let us see D we have now. Okay, so this is one way you can write. Another way also is there. Okay, dV, so that's equal to 2L. Let's substitute in C. So we get here the dipole moment, magnetic dipole moment is equal to, okay, so D is equal to 2L we don't know. So we get here 2, I like front, Qm into L. Okay, this is another way of writing it. Okay. So let us see now what is the S unit of this. Okay, the S unit of this dipole moment. Okay, the S unit we say that is ampere meter square. Okay, ampere, A stands for ampere. Okay, meter square. That's the S unit of this quantity here, magnetic dipole moment. Okay, next we'll see what's meant by magnetic field. But even before going that, we'll just see this definition here. So magnetic dipole moment is defined as the product of the pole strength and the magnetic length. Okay, so this is the definition of the magnetic dipole moment. Now let us study what's meant by magnetic field. Okay, around the magnet we have a magnetic field. Okay, let's see this thing. So let me take a magnet here. This is north pole and this is the south pole. Okay, so around the magnet we have a magnetic field, right? North, south, inside. Okay, so clear. Okay, so there's a magnetic field here. Okay, we can't see it, but we can feel it. Okay, with the help of an iron nail. Suppose you bring an iron nail or another magnet here, what will happen? It will be attracted. Okay, if you bring another north pole there, it will be repelled. Okay, so I'll take an example here, second one. I'll take another north pole here, this way, south pole. So what will happen? This will repel here. Okay, in this region only. If you go very far away, it won't repel. So magnetic field is a region around a magnet where the magnetic force can be felt. Okay, next we'll see how to define it. Okay, so we have learned electric field also now. Same way we have defining magnetic field. Okay, for the magnetic field formula, that is a symbol that is B. Okay, magnetic field symbol is capital B. Okay, so we learned now in Earth's magnetic field. Okay, we use the term B here. That means magnetic field. Okay, so magnetic field is defined as the force experienced by a magnet, okay, of unit pole strength. Okay, so this thing here. So B means the magnetic field, F means the force, Qm means the pole strength. Okay, so let's see the formula here. We'll write what each term means. B means the magnetic field. F means the force and Q means the pole strength. Okay, magnetic pole strength. Okay. Let's see what will be the S unit for this. I'll write this side. The S unit for this term will be Newton. Okay, because forces are Newton. Then pole strength will be ampere per meter, ampere meter. Okay, so Newton by ampere meter, because Q means pole strength. So you take this up. So what we get is Newton. Okay, then ampere goes up now. So ampere power -1, meter power -1. So this is the S unit of the term here. Okay, so I'll drop this term here. So now you know how it comes. Okay. I write on top Newton, ampere inverse, and then meter inverse. Okay, that is the S unit for magnetic field. Now let's go to next one type. That is types of magnets. Okay, that you're very familiar with. Okay, I'll write now. Let us now study the types of magnets. Okay. Magnets are defined two categories, that is natural magnets and artificial magnets. Okay. Natural magnets that are we find in the ground. Okay. So example, that is iron, cobalt, nickel and their ores also. Okay. So nature, you see that metals will be in a mixed state only with other things. Okay. You learn chemistry also. So metallurgy, you learn that. So those kind of things are called as natural magnets. Okay. The thing about natural magnets is they are very weak only. Okay, they are very weak, and then they are of irregular shape. Okay, and the size also. So we can't make different things with the help of them. Okay, but that's how they found the magnets also. Okay, natural magnets were there. Now let's see artificial magnets. They are human made. Okay, they have desired shapes and sizes and strength also. Okay, so whichever shape we want, we can make the magnet, and we can make different strengths also. So suppose you have a magnet like a rectangle shape or a cylindrical shape, then you can say it's a bar magnet. Okay. Then you learned in lower class about the horseshoe magnets that are okay, dumbbell shaped magnets, cylindrical magnets. In speaker you have the ring shaped magnets. So those are all mainly made up of artificial things only. Okay, man-made things. So and man-made metals there. So these are two types of magnets there. Now let us study about the different properties of magnets. Okay, so first one is that you take a magnet, okay, and then tie it with a string and leave it. It will always show the north south direction. Okay, so it's used in the magnetic compass also, we learned. Next, second property, we see that a magnet is there. Around we keep a paper there on top of it, and we keep sprinkle some iron filings. And then if you tap the paper, the iron filings will arrange the pattern. Okay, this shows that magnets can attract magnetic materials like iron, cobalt, nickel. It can attract. Okay, so a magnet can attract magnetic materials which are kept nearby. That's the second point. Then third point, you see we have big magnet. Okay, you break the magnet two pieces. Okay, even if you break the magnet two pieces, again you get two small magnets there. Okay, so these two small magnets also will have north pole and south pole. This also will have north pole and south pole. You cannot separate north pole separately, south pole separately. Okay, so it's like that way. So you get two individual magnets, they say. And fourth point, you see, so this is the south pole and this is the north pole. Okay, so magnetic field lines, each line is called a magnetic field line. It starts from north pole and goes to south pole. We'll come to it a little later. But in this point, you see, mainly we have this is north pole and this is south pole. Okay, it has a pole strength QM. This north pole has a pole strength QM. Okay, so the pole strengths of the north pole is equal to pole strength of the south pole. That means the two poles have equal strengths there. Okay, north pole and south pole have the two equal strengths. Next one, we see the fifth point here, geometrical length. Okay, I'll come to this side. Okay, so now we take a magnet there. Okay, this is north and this is south here. You can take the full length there. Okay, if you measure using scale, that will be the geometric length. Okay, but if you see exactly, the north pole is inside the magnet. It's not outside. Okay, so it's slightly inside there. So when you take this length here from this north pole, this dot to this dot, okay, so you can see that will be too small. Okay, this is called as a magnetic length. Okay, magnetic length is smaller than the geometric length. So we divide this magnetic length by the geometric length. Okay, so we divide this, we can see we get 5 by 6. Okay, because magnetic length is small, we say. So we get 5 by 6. 5 by 6 comes to be 0.833. Okay, so these are the different properties of the magnet.